Good evening, everyone. So good to be with you again tonight. Tonight we're going to be starting a new chapter. It's chapter 6, Radio Circuits and Systems, and we're going to start putting the pieces together. We've talked about various individual items, and tonight we're going to start putting them into circuits, things that make ham radio work. It's interesting, this chapter is tied with Gary's chapter 9 on antennas and feed lines for being the biggest chapter in the book. So this is going to be covered over 2 nights, this week and next week. And Gary gets to chapter 9. Of course, he'll do that in 2 weeks as well. So a lot of meat here. Now there's a few calculations tonight, but they're very simple. They look a little bit scary in the book, but I'll share some approaches that'll make those really easy. Most of the questions are fact-based. So I'll try to present maybe a little bit more theory than what you need for the questions, just so that they'll all fit together and make some sense. So amplifiers, there's tons and tons of amplifiers used in ham radio. We see them at RF stages in the front of a receiver, intermediate frequency chains, audio amplifiers. Here's a high power KPA 1500 from Elecraft. Here's the lowly 741 op amp. We're going to be talking about op amps tonight. We're going to be talking about gain. I like to think, I think it was Kassler that said that thinking of amplifiers, that means loud. You start out with something small and make something louder. Amplifiers have input and output impedance characteristics that'll help match a radio to a feed line, for example. And there's all kinds of active components. We'll be looking mostly at transistors, but we'll be mentioning tubes and ICs a little bit as well. Before we get into it, I thought it would be helpful to review a couple of concepts we're going to run into in the following slides. First one is on voltage dividers. So we've got a 10-volt battery here. We've got 2 1K resistors, and this is all reference the negative pole of the battery, or ground if you want to call it that. So at the top here we've got the 10-volt applied circuit voltage, and then we're going to have exactly half of that voltage across these 2 1K resistors. So you could say we've got a voltage drop of 5 volts across each of these resistors. Fairly simple concept. So this is DC. Now let's consider an AC example over here. Now we're going to have 10 volts of AC. We're still going to have the 2 1K resistors, but I've added something here, a 25 microfarad capacitor. And at 1 kilohertz, the reactive, or the capacitive and reactance is 6 ohms. So from an AC point of view, we effectively have a 1K resistor and a 6 ohm resistor, or 6 ohms in parallel with 1K, something just right at 6 ohms. So what's happening here, the addition of this capacitor that's shorting out that AC voltage to ground winds up putting almost the full supply voltage at the bottom of this resistor. And we're going to see when we get into the common emitter amplifier that this is significant. You see this a lot. So just kind of wanted to give you this review before we get into the next idea. Dave Kassler talked about 3 terminal devices, and that picture fits really, really well for the initial part of our presentation tonight. So a 3-terminal device has got 1 terminal that's common to both input and output. So the input is on pins 1 and 3, terminals 1 and 3. The output is on 2 and 3. Terminal 3 is shared between input and output. So it's real helpful to visualize transistors as a 3-terminal device. So let's get to our first one here, the common emitter. And what I'm going to be doing is rotating this transistor through the 3 possible positions of input and output. The reason that common emitter is in blue is because there's a pool question that specifically asks you to identify the common emitter configuration. And I'm also going to be giving you a trick or a shortcut for doing that. So you might be wondering, well, why do we need all of these different configurations? Well, each configuration gives you a slightly different set of technical parameters that you can pick from. The common emitter is by far the most common. You'll see that most often. The next one, you can see that we've just rotated the transistor clockwise. Now we've got a common base. In case of the common emitter, we've got the emitter common between input and output. The common base, the base is the element that's in common between input and output. Then we've got the common collector. This is also called an emitter follower. You notice we've rotated the transistor another way around the circle. So we've got the collector as the common item. And the output is from the emitter. So that's why it's sometimes called an emitter follower. Now these have parallels with the other type. We're looking at junction transistors here. This is a field effect transistor with a source, gate, and drain, and the same configurations can be used there. Likewise with a vacuum tube. And we still have vacuum tubes around today and power amplifiers for transceivers. And we've got the same idea here. You can have a grounded grid or a grounded cathode amplifier. So each of these have slightly different characteristics in terms of impedance, and we'll get into that a little bit more. First of all, the common emitter circuit. Now, what I'm sharing here is a highly abbreviated form of what's in our license manual. The license manual is excellent. If you're really into the details of the electronics, by all means, go through that and follow it. But I'm just going to be offering the parts that you really need to know that relate to the pool questions. We'll be focusing on that with a little bit of extra along the way. So common emitter, the input is to the base. Here's the base. Output is from the collector through a resistor. This configuration provides the highest gain of the three types. Now, the first pool question, they ask about the purpose of R1 and R2. You might remember from our discussion on semiconductors that a transistor, when it's turned on, will have a voltage between the emitter and base of about 6 to 7/10 of a volt DC. So the purpose of R1 and R2 is to establish a voltage divider so that we get the proper voltage on the base of the transistor so that we can turn it on to one level or another. And there's different places where you might want to have that set. We'll talk more about that also. But R1 and R2, their purpose is to provide voltage divider bias for the circuit, DC-wise. The purpose of R3 is called self-bias. Now what happens with a transistor, when it starts to conduct a lot of current, it gets hotter and hotter and warmer. So if more current is flowing through the collector to emitter, in other words, the transistor is turned on harder, that's going to drop a larger voltage across R3. If we increase the voltage across R3, that's going to make the emitter a little bit higher relative to the base, and it will turn the transistor off to some extent. We don't want to shut it off completely, but that's kind of a self-regulating device so that as the transistor gets hotter, it conducts harder. That's just a normal part of the physics of transistors. So, and it's a vicious circle because when the transistor gets hotter, it conducts more, and it conducts more, and it gets hotter, and it conducts more, and it gets hotter, and eventually it'll burn out. So that's what this self-bias concept is. It tends to adjust the transistor's how much current it's conducting. So walking through the flow here, we've kind of looked at some of the DC aspects, the bias, the voltage divider. From an AC point of view, we're feeding a signal in here, and it's coming through a capacitor. The reason that we're using a coupling capacitor is that we don't want the circuit before this stage to change the bias conditions on the transistor. So as you may recall, a capacitor will not pass DC, it'll just pass the AC. So the signal will come through, it won't upset the bias that we've set on it. And C2 is the output coupling capacitor. Again, we don't want to take the DC that happens to be at this point and pass it through to the next stage. Remember when I showed you the capacitor that bypassed the lower resistor in that first diagram I showed you? Well, here we've got one right here, C3. What that will do is basically short out the AC voltage across R3, and the entire voltage, signal voltage, will be developed across this transistor, giving us a much higher level of output. So trying to tie some of these concepts together for us. So let's consider this picture here. If you want a transistor to faithfully reproduce everything on its input, in other words, you want it to operate in a linear manner, any change in the input results in a corresponding change in the output, you need to set the bias to turn the transistor on about halfway. That way, as the signal swings above and below that point, the output will be faithfully reproduced. If you set the bias too low, near cutoff or saturation, you'll have severe distortion of that incoming waveform. And as we saw, R1 and R2 form that voltage divider bias to turn the transistor on about halfway. That happens to be for what we'll call a Class A amplifier, which we'll talk about a little bit later. So let's assume that we've got a circuit that's designed for a gain of 100. And if the base, I'm talking AC signal levels here coming into it, if the base is moved up by 1/100 of a volt, let's say that the collector changes by about 1 volt. That would be a gain of 100. 100 times 1/100th is 1. So that's the concept of gain. Now let's assume that the DC bias is set as it was in the previous slide. All right, and here we're just seeing a few more details. First of all, notice that the signal rises, goes through 0, falls, comes back. What does the output look like? Well, it's the reverse of that. So a common emitter amplifier is an inverting amplifier. And that's not true of the other types. Practically speaking, it won't make much difference in your circuit, but it's just something to be aware of. So input at the base, let's say it's 4.6 volts. That's the DC level. Output of the collector is going to be varying between, it'll be varying 100 times that. As we mentioned, the capacitors look like open circuits to DC, so they provide DC isolation. That's the input coupling capacitor and the output coupling capacitor. And I've got a little spoiler alert. I'll be showing this in another slide here in a minute. Notice that these capacitors, the way they're drawn in the circuit, are one right above the other. And for the purpose of our pool question, when it asks what kind of a amplifier is this, that's the shortcut that you can use to say, oh, this is the common emitter configuration. If you wanted to know from an electronics point of view, you'd have to figure out, well, the output is really, the input and the output, is shared. The emitter is the shared element, making it the common emitter. And as I mentioned, the high value cap will look like a short circuit to AC. So the entire output is developed up here. You'll have a lot more output out of this circuit if C3 is in place. Common base. All right, we've rotated the transistor around. This is the configuration. Notice here that the signal input and signal output are tracking each other. You'll notice that there isn't any blue text here. They don't focus on this very much in the pool. So the input is on the emitter. You see that? Output is on the collector. It's a low impedance input, high impedance output. So here we've got a case where this circuit configuration can be used for impedance matching. It's primarily used as an impedance converter. Common collector. Okay, a few pool questions here. It's also called an emitter follower. You can see that the signal is, the output signal is off the emitter. That's where you get the term emitter follower. And again, the input and output signals are in phase. We see the output coupling capacitor. Just trying to, I think we can kind of understand, or we're beginning to understand what the purpose of all of these parts happen to be here. This is the power supply positive, which is normally an AC ground. They also bypass it just to make sure that it's at ground. This is often used as a buffer amplifier. For example, when we have an oscillator, normally you don't want to have an oscillator circuit directly drive a stage beyond it that might load it down. So it's very common to use a buffer amplifier between a sensitive oscillator circuit and everything that follows. And we kind of saw one purpose of R before, and in this case it's referred to as an emitter load resistor. Before it was provided, its purpose was to provide self-bias. Identifying the common emitter configuration. Here it is, and the little spoiler alert that I gave you. If you can remember when you get to the pool question that the diagram has two capacitors that both go in this direction, one off the collector, one off the emitter, you can instantly identify that as the common emitter by the way that they've drawn it here. In all cases, it won't appear this way in other circuits. You could figure out, well, you know, what is the input? It's between the base and the emitter. What's the output? The output is actually common emitter. You'd think it would be on the emitter, but the way the circuit's configured, the emitter current actually appears over here. Vacuum tubes can be plugged in exactly the same way. The plate corresponds to the collector, plate, collector. The grid corresponds to the base, and cathode to the emitter. So we have common cathode amplifier, high input impedance and power gain. You'll see this in amplifier circuits. And then the grounded grid, a couple of pool questions there. The grounded grid has low input impedance. So low input impedance on a power amplifier that's after your transceiver feeding your antenna, because your transceiver, its output is 50 ohms normally, you would want a low impedance input to your power amplifier. So these are, this configuration often is used in that case. There's just one pool question on grounded grid amps. You need to know what has low impedance. And right into some exam questions. Now, I really covered that in a hurry because I was focusing on what we would need for the pool questions. Much more detail in the manual if you care to get into it. And I know many of you will not. Those that are interested, it's there for you. So in figure E7-1, what is the purpose of R1 and R2? You can unmute, give us about 3 seconds, and give us an answer.
Voltage divider.
Voltage divider bias, correct. What is the purpose of R3?
Delta.
Delta self-bias, correct. As the transistor conducts harder, it'll raise this voltage and turn off the transistor slightly. What type of amplifier is shown in this figure?
Charlie.
Charlie, it's a common emitter. Yep. And the shortcut that I gave you. What is characteristic of an emitter follower or common collector amplifier?
Delta.
It is delta. Input and output signals are in phase. That's true of the common collector and the common base, but they only ask about this one. What is a characteristic of a grounded grid amplifier?
C.
Charlie.
Charlie, low input impedance. A good match to a transceiver output. Now that wasn't so hard, was it? We cruised right through that. There weren't a lot of pool questions. The theory behind all of this would be, as Gary likes to say, an entire semester in college, but we've focused on what we need to know. Operational amplifiers. These are like, I called these the Swiss Army knife of amplifiers. Now, previously we were seeing discrete amplifiers. That means each part was individually shown. A transistor is one part, the resistors and capacitors. In this case, an op-amp, all of that is contained within a package. So what can we do with these things? Well, it can be an AC amplifier. It can be a DC amplifier. It can be a filter that can be configured as filters. If you feed a certain amount of the output signal back to the input through a network, either capacitor, inductor, or capacitor and resistor, it can operate as all kinds of things. It can work as a comparator, where you take the two input voltages and see if one is greater than another one. If it is, it'll switch. It can do impedance matching. It can be configured as an oscillator. So all of these things can be done with an op-amp. And they're easy to, they're cheap. They're less than $1, the 741. So if you're interested, you can play with these on a perf board, or a board that lets you easily connect some things to it. It's fun to experiment with these. There are a humongous number of applications. Now, in the beginning, the reason that these are called operational amplifiers is because you can configure them to do mathematical operations. In other words, a change on the input could appear on the output as the square or square root of what is happening on the input. So if it moves a small amount, you know, the square of that amount could appear on the output in terms of the voltage that you would see. Logarithms, just all kinds of mathematical operations. So in the early days, that's what they were using these for. Now here's some words that are gonna scare you. So what is an operational amplifier? It's a high gain, direct coupled differential amplifier with very high input and very low output impedance. Well, that's a real mouthful. Okay, let's unpack that a little bit. The high gain part is impressive. These things can have a gain of over 1 million, which is fabulous. Now, direct coupled differential amplifier. Now, differential means that you're looking at the difference between these input signals. We've got the non-inverting input, this one plus, and the inverting input, the minus. So differential amplifier means it's amplifying the difference between these two pins. Very high input and very low output impedance. So high input impedance here, a very low output impedance. Now it's direct coupled, it says direct coupled here. That means it'll amplify DC as well as AC signals. So a 1/10 of a volt DC will appear as some value of DC over here. Also notice if that change is here, let's say we go up a 1/10 of a volt and the gain is 10, we're going to be, the output is going to be it'll be 1 volt, but it's going to be negative because that input is on the inverting input. We'll expand on that in a bit. 2 inputs, inverting, non-inverting, and it amplifies the difference between. So with that explanation, hopefully these crazy words will make some sense, and when you get to the pull question that's related, you'll understand what it's saying. So now we're going to talk about the ideal op-amp and then what we're talking about in the real world. The ideal op-amp will have infinite input impedance. Of course, you know that can't be, but it can be extremely high. It's going to have 0 output impedance, infinite voltage gain. Gain does not vary with frequency, and 0 output when the input is 0. So let's see what in the real world what happens. We don't have infinite input impedance, but we have very high input impedance. zero output, we're going to have very low output impedance. And notice the blue text. Infinite voltage gain, well, it can be as high as 120 dB in what's called an open loop configuration. We'll look at that configuration in a bit. That's over 1 million. Amazing when you think about it. The gain does not vary with frequency. Well, in the real world, the higher the frequency gets, the gain starts decreasing. And most op amps, the 741, for example, that we've been referring to, are pretty much audio devices. They might work up to a few tens of kilohertz. You can probably get military parts that go much higher than that. But generally speaking, you'll see these, most op amp applications are in audio or low frequency applications. Zero output when the input is zero. Well, actually there's going to be some output with zero input. So we have the ideal versus the practical. Now here's a circuit. The gain of an op amp is determined by the ratio that this is called a feedback resistor. It's going from the output back to, in this case, the inverting input. RF stands for feedback resistance. This is the input resistance. So the gain of this circuit is the ratio of the feedback resistor to the input resistor. And here's a formula saying the absolute value is RF divided by R1. Kind of a weird formula. But in doing the gain calculations, it's going to be extremely simple. It's one divided by the other. In this case, the circuit is using the inverting input, so the result will be negative. Be the opposite. It'll go in the opposite direction of what's coming in on the inverting input. Now, if we put a capacitor across the feedback resistor, it will make the frequency response of the circuit a low-pass filter. So depending upon what you put in this feedback loop, combinations of capacitors and resistors and I suppose even inductors will completely change what the circuit does. But in this case, they're showing us that a capacitor will make it a low-pass filter. Now, closed loop, I mentioned open loop before. Closed loop is when we have a feedback resistor. Open loop is when we do not. So this is the closed loop. The gain is controlled by RF divided by R1. And here's a calculation that we can do. I'm not going to actually show this with a calculator cam, but you can do it on your own calculator if you want, because it's so simple. So if the gain is RF divided by R1, if RF is 68K, R1 is 1.8K, you need to have these in the same values, or the same units. So 68K divided by 1.8K would be 68 divided by 1.8 is 38. So the gain of this circuit with these resistors is 38. So the output's going to be 38 times greater, the output swing, than what you see on the input. Now here's a trick that will help you. For the exam, it's always the bigger value divided by the smaller value. So you don't have to remember, is it R1 divided by RF, or is it the other way around? This trick will help you for all of the pool questions where there's a gain calculation involved. Bigger value divided by the smaller. Make sure that the units are the same, kilo to kilo. Here's another one. We've got RF is 10,000. R1 is 1. It's easier to think of that as 10K and 1K. The gain is going to be 10 over 1, or 10. Okay, now this is the trickiest pool question on op amps, so kind of follow along with me on this. So let's use an input voltage of 0.23 volts DC, the input, times 10, which is the gain, is going to give us 2.3 volts on the output. But notice that the input is on the inverting. We're using the inverting input, so the output is going to be negative or minus 2.3. So you may be able to just remember that that's the case when we see the pool question, but I thought it was important to kind of walk through how they got there. And it reinforces all of the things that we talked about. So this is the most complicated question we have, and it's really pretty simple, I think you'll agree. The thing that trips people is the voltage is going to be negative on the output for a positive swing on the input. In this case, it's amplifying DC. All right, now what have we got here? We've got an op-amp circuit, and there is no feedback resistor. That is the open loop configuration. And what we're showing here is an open loop comparator. Well, what does that mean? When the input voltage crosses the threshold voltage, the comparator changes its output state. All right, well, how do we know what the threshold voltage is? Well, remember we were talking about voltage dividers? Well, here we've got a voltage divider, R1 and R2, setting a specific voltage on pin 2. So when the input voltage on pin 3 crosses the threshold voltage that we've set on pin 2 with these bias resistors, and you could call them that, or voltage divider resistors, the comparator changes its output state. So it'll snap from high or low on the output. Hysteresis. Now hysteresis is an interesting concept, is provided by R3. So when we force this comparator to switch, we want to exceed the value that caused it to do that before it switches back to the other one. The best analogy I could think of for this was an air conditioner running in your house. Let's say you've got an air conditioner and you've got your thermostat set at 70 degrees. Well, it's 75 degrees in the house, so the air conditioner is going to come on and start cooling your house until it gets to 70 degrees. And then at 70 degrees, the air conditioning system will turn off. Well, if it gets to 70.001 degrees in the house, you don't want it to come back on again, or the thing is just going to be flipping on and off continuously. You'd like your room temperature maybe to rise to 72 degrees or 73 degrees before it comes back on and brings it down to 70. That's the concept of hysteresis, going a little bit beyond what it would normally take to cause the switch to occur. And we can see that that happens because the voltage divider value that's provided by R1 and R2 is going to be offset a little bit by the output going low and reducing that voltage, causing the input needing to go a little bit higher than it would have to change state. And this is often used to prevent noise. In other words, if there's just a very slight difference between the inputs of the op-amp due to noise, you don't want that noise to be causing the circuit to flip on and off continuously. So hysteresis prevents noise from causing unstable output signals, rapid continuous switching. So the definitions, I'll share a few. Here's the same circuit we just saw. For open loop, there's no feedback resistor. Also, a parameter that's measured in the open loop configuration is input offset voltage. I think I mentioned in the ideal op-amp that we considered that if both inputs were the same or not connected, the output voltage would be 0. Well, due to the high gain of the device, that's never going to quite be the case. So input offset voltage is the differential input voltage needed to bring the open loop output voltage to 0. So to get this to actually go to 0, there will normally be a slight difference between these two in order to make that go to 0. And that's defined as the input offset voltage. Now in our book, and the only reason I mention this is because we've had a student or two ask about this in the past, on page 6-7, or figure 6.7 on page 6-9, there's a reference to a virtual ground, and it points to pin 2. You don't need this for the exam, but if you're curious about what that means, I've given you a link. It's kind of beyond the scope of what we're talking about tonight, but if anybody's read that and wonders about it, I wanted to give you a resource where you could resolve that question. Not needed, not required. Another concept, gain bandwidth. Now this is the frequency. Remember we saw that the ideal amplifier wouldn't change its gain with frequency, but a real one, the gain tends to go down with increasing frequency. Okay, so gain bandwidth is the frequency at which the open loop gain equals 1. So normally op amps have a fairly high amount of gain, but if you keep raising the frequency, the gain is going to become less and less. And when we get to the point of unity gain, that means the input signal and the output signal are exactly the same. That's the gain. That's when the gain bandwidth equals 1. So a tenth of a, or let's keep using a tenth of a volt. We have a tenth of a volt here. The gain is going to be much, much higher over here, but as you keep raising the frequency from 10 kilohertz to 20 kilohertz to 50 kilohertz to 100 kilohertz, eventually this output is going to be falling until it gets to be a tenth of a volt. That's unity gain, which is the definition of open loop gain equals 1. So let's see if we can make sense of this now. Gain bandwidth is the frequency at which the open loop gain equals 1. The reason I'm giving you that background is so that you can better relate to the pool question. And some calculations. Okay, what is the typical output impedance of an op amp? There's kind of a trap here, but let's see if you can get it first. Typical output impedance.
A.
It is A. Now the trap that they actually put some values in here. So somebody could look at this and say, okay, well it's very low, so that it must be the 100, okay? But that's not where they're coming from. They want very low. So don't let that trick you. Very low. What is the typical input impedance of an op amp? The same logic applies.
Very high.
Very high, right. In our ideal, it was infinite. What is the frequency response of the circuit in E7-3 if a capacitor is added across the feedback resistor? Well, I didn't put the diagram in here. I'll have to fix that for the next time. But remember, we talked about putting a capacitor across a feedback resistor. What will that make the circuit do?
Low pass.
Bravo.
Yes, I was too fast on the finger, but you were saying it at the same time. Low pass filter, correct. And the main point of that is you can put all kinds of things in that feedback loop to make the op amp do all kinds of interesting things. Okay, what is meant by the term op amp input offset voltage? You might have to give yourself a minute to read through these.
Charlie.
It is Charlie. The differential input voltage needed to bring the open loop output voltage to 0. What is the gain bandwidth of an operational amplifier?
Bravo.
Well, it's not Bravo. Oh, it is Bravo. I'm sorry. I was off at lost in space there someplace. It is Bravo. The frequency at which the open loop gain of the amplifier equals 1. Yeah, I was looking at D and daydreaming. So you're right. It's B. Bravo. All right. Here's a calculation, and you can do this on your calculator in about 5 seconds. What is the voltage gain? What voltage gain can be expected from this circuit when R1 is 10 ohms and RF is 470? Remember, the bigger divided by the smaller.
C.
Charlie.
It is C, Charlie, yeah.
Charlie.
Yeah, Charlie. How does the gain of an ideal operational amplifier vary with frequency? Now notice the word ideal here. so be careful not to get tripped.
D.
Delta.
Delta does not vary with frequency. A real one, the gain goes down as frequency increases. Okay, here's another calculation. What will be the output voltage? And this is the one that was a little bit complicated that we walked through. Output voltage, if R1 is 1,000, RF is 10,000, 0.23 volts on the input.
Charlie, isn't it? Delta.
It is delta, and let's just talk quickly through this. 10,000 divided by, 10,000 divided by 1,000 is going to be a voltage gain of 10. So if we got 0.23 in, we're going to have 2.3 out. That's the voltage gain of 10. And it's going to be negative. So 0.23 times 10 is 2.3. Because we're on the inverting input, the output's going to be negative. Yeah, this is the trickiest one that we have. So you can just you can kind of remember how we got there, which is valid, not too difficult to work through. Or you can just remember. Now, notice that they give us all kinds of ways to get this wrong. They get positive and negative and so forth. So you have to slow down when you hit this one. Here's another voltage gain problem. And you can calculate this and tell me what it is. I hear key clicks in the background.
Charlie.
Charlie, yep. It's 68 and divided by 1.8 gives you 38. So in the license manual, these look a lot harder than that, but that's all that we have to worry about to be able to solve these problems. Here's another one. Let's see what this one is. They really like these. And again, because of the section that they're in, or the group that they're in, you're only getting a maximum of one of these on your exam, if you get any.
Bravo.
Bravo, it's 47 divided by 3.3, which is 14. Bravo is correct. What is an operational amplifier? These were those crazy words that we talked about back in the beginning.
Alpha.
It is alpha, high gain alpha, correct. A high gain direct coupled differential amplifier with very high input impedance, very low output impedance. What is the function of hysteresis in a comparator?
Alpha.
It is alpha, to prevent input noise from causing unstable output signals. What happens when the level of a comparator's input signal crosses the threshold voltage?
B.
Bravo.
Bravo.
Correct. The comparator changes its output state. Good. That's it for operational amplifiers. Moving right along. Amplifier classes. Now this is an area where students have had a little bit of trouble in the past, so I try to show this 2 or 3 different ways, and you can pick the one that works for you. Okay, so here's a visual. Now we're showing an input waveform being applied to an amplifier, and then the classes are here. What this is telling us that the amplifier, for a Class A amplifier, for 100% of the input waveform, it's going to be conducting. In other words, it's going to be faithfully reproducing the input waveform in its output. So if the amplifier has a gain of 10, for example, we're not talking about op amps now necessarily, but if it has a gain of 10, that gain will be faithfully reproduced over the entire 360 cycles of the input waveform. Class B, we're only going to be amplifying half of the input waveform. And you might be wondering to yourself, why in the world would we ever want to do that? Well, we'll answer that. Class AB, we're amplifying greater than 180 degrees of the input waveform, but less than 360 degrees. Now in Class A, we're amplifying all 360 degrees of the input waveform. Class B, half of that, 180 degrees. In Class AB, it's more than 180, but less than 360. And then Class C, we're just going to be conducting on a small part of the waveform. And this all has to do with the way the bias is set between cutoff and saturation we saw in our transistor diagram. And then we've got Class D. This looks like a real strange bird. We've got a waveform, in this case a triangle waveform on one input, and then we got the signal that we're wanting to amplify here. It's going through some electronics, resulting in some pulse width modulation output that is then smoothed by this low-pass filter to give us a nice clean output signal. These are highly efficient because the outputs are normally at full saturation or full cutoff. The amount of power that's coming out of it is determined by the width of these pulses. Because this looks horrible here, that's why we need a low-pass filter to smooth that out. So that was basically version 1 of what we're talking about. Let's look at it another way. Oh, before I do that, there's one pull question that asks about an AB amplifier. And you need to know that it's greater than 180 degrees of the input waveform being amplified. That's past the zero crossing point, but less than 360. It'd be a pull question like that. So here's a kind of a summary, just showing it to you in a different way. So Class A, going to be conducting approximately halfway, or the way that the amplifier is going to be set, it'll be set approximately halfway between saturation and cutoff. So saturation was when the transistor is turned on fully. It can't be turned on any harder. Cutoff is when it's not conducting at all. So someplace in the middle of that is where we need to set the operational characteristic of the amplifier, or the load line, if you want to call it that, to get Class A performance. Class B, bias is set at cutoff so that only 1/2 of the waveform is being amplified. Only, let's say, the positive going peak will cause that to, it will cause the transistor to conduct. AB operates between 180 and 360. In Class C, bias is set well into the cutoff region. And Class D uses switching technology to achieve high efficiency because the transistors are normally fully cut off or fully saturated. And it needs a harmonic filter to remove, it needs a filter to remove harmonic content. So just take a second and try to absorb the blue text here, because that's going to show up for you. Here's an expansion of the chart that I showed you. The saturation region of an amplifier or a transistor, that means it's fully conducting. Cutoff means it's set so that it's not conducting at all. And for a Class A amplifier, you'd want it to be operating in this region. So Class C limits are way down here, near cutoff. Class A or AB are in this region. And that kind of describes what we're dealing with. So here's another take. Okay, this is from Kessler. He equated this to a flywheel. So here's a flywheel that's kind of spinning around. For Class A, the signal is always pushing on the flywheel. It's helping it all the way around, all 360 degrees of the input waveform. Class B, you can see we've just got half now. Class B pushes the flywheel half of the time, and Class C pushes the flywheel less than half of the time. But because it's a flywheel, it will, flywheel, remember, is a heavy piece of metal, and circular metal. like a wheel, and it's going to continue to turn even after you've taken the push away. And that's going to be very helpful in certain radio applications. So if we think of FM, frequency modulation, that's normally a full carrier mode. So we'd only need a slight push, and it wouldn't distort the relationship in any way. For single sideband or AM, where the sensitivity, the amplitude has to be reproduced exactly, that can only be done with a Class A to avoid distortion. You might remember when we were talking about tuned circuits, the coil and capacitor storing energy and giving it back. Well, that also relates to this. If the coil and capacitor are continuing to exchange energy, circulating current, when you take away the input, it's going to continue providing, the circulating current is going to continue to be there, and the signal output will remain even though it's slowly reducing. So that all relates to this picture. So this is just a review. We've already seen this slide, but I wanted to put it up again because all of these are going to appear in pool questions. I'll give you a second to read that. All right, and then we'll move on to why would you want to use these different amplifier classes? Well, for CW or FM, those are full carrier modes. In other words, if you've got a 100-watt transceiver, when you're transmitting FM, you're going to be transmitting 100 watts continuously. For CW, continuous wave, Morse code, when the key is down, you're going to be at 100 watts. So there's not a big concern about the little dips that may occur for Class B and C operation. For AM and single sideband, a linear amp is required. Linear means that the input is faithfully reproduced in the output. And the only way you can do that normally is with a Class A amplifier. Using a Class C amp for amplifying single sideband phone signal will result in distortion and excessive bandwidth. Well, how can you tell how linear your amplifier is? There's something Gary's going to be talking about in 2 weeks in test equipment called the two-tone test, where you apply 2 tones to the input of an amplifier and then look at what you see on the output. So this one is relatively good. These are the 2 tones, and these are called the intermod products. They're down 1 to, looks like close to 30 dB down. Here's one that's generating a lot of distortion, and these intermod products are much, much higher. This is a circuit setup for doing that called a two-tone test. I won't say any more than that because I'll be stealing Gary's thunder for 2 weeks. But that's how it's measured. Questions. What portion of the signal cycle does each active element in a push-pull Class AB amplifier conduct? We didn't really talk about push-pull, but AB, we did say that there are, one of these answers will apply. Class AB.
A.
It is alpha, more than, yeah, correct, more than 180, but less than 360. What is a Class D amplifier?
Alpha.
Alpha, an amplifier that uses switching technology to achieve high efficiency.
And in VOA, we used pulse width modulation amplifiers in our high-powered transmitters, some of them, simply because it was much more energy efficient to get modulation from these amplifiers than it was to use a big modulation transformer.
And why would you care?
Because power is expensive.
Exactly. Yeah, I think Gary told us in another class that the big expenses in a high-power broadcast station are power
And personnel.
And personnel, yep. What circuit is required at the output of an RF switching amplifier?
Alpha.
Yep, got to remove that, that chopped up looking output, filter to remove harmonic content, smooth it back into a sine wave or whatever was coming into it. What is the operating point of a class A common emitter amplifier?
Alpha.
Alpha, about halfway between saturation and cutoff. That gives you a faithful reproduction on the output of what's coming in the input. Which of the following is which of the following is the likely result of using a Class C amplifier to amplify single sideband? I just heard some noise.
Delta.
Delta, signal distortion and excessive bandwidth.
That was my signal distortion.
Oh, okay. Gary was making distortion. E7B08. Why are switching amplifiers more efficient than linear amplifiers?
B,
Robin.
Yes, the device is at saturation or cutoff most of the time. Okay, now the next section is section 6.2, signal processing, oscillator circuits, and crystals. We're going to do this after our break, and if we have time at the end, we have some other interesting things to talk about. So right now we're on track, having a little time at the end. So take 5 minutes and go pet your goldfish, or get a drink, do something, get your mind off this, and we'll be back in 5. Okay, well, we're back after our break. Hope you had a good time during your break. We're going to be looking at section 6.2 now, continuing our discussion on circuits used in amateur radio. First thing we're going to talk about is oscillator circuits, and we're going to jump around a little bit. We're going to tell you about some instability and bad things that can happen with oscillation, and then get into the good things that we can do with oscillators. So first of all, what will make a circuit oscillate? Well, if you've got an amplifier and the gain is greater than 1 and the feedback is in phase, the circuit will oscillate. That means it'll ring. It'll just continually be generating an output based on the output being fed back to the input. So those are the conditions. So you want to have nice clean signals. Some people call children parasitic oscillations. Well, you're a kid that's pretty messy. We don't want to have messy signals. So parasitics are oscillations that are not related to the operating frequency of an amplifier. They may be above or below the operating frequency. So parasitic oscillations are bad. Excessive gain or positive feedback may cause amplifier instability. You've probably all been in an auditorium where they've got a PA amplifier, they've got it turned up too loud, and it starts to howl. Well, that's excessive gain and positive feedback. The microphones are getting into the speakers and causing the howl. And in an RF amplifier, unwanted oscillations can be prevented by installing parasitic suppressors and or neutralizing the stage. And I'll have a picture of that coming up. And there's a case where, well, let me talk about this first. The RF power amplifier can be neutralized by feeding a 180-degree out-of-phase portion of the output back to the input. And here's a diagram. This is a tube-type amplifier. And we've got some capacitance internal to the tube, that's why it's in dashed lines, between the grid and the plate. Well, that feedback, or that capacitance will be providing some positive feedback into the circuit, and it's possible that the amplifier could oscillate. So the way that they get around that, there's what's called a neutralization procedure, which should be done anytime you change a tube in a power amplifier. That's CN, capacitance for neutralization, and it takes a signal that's 180 degrees out of phase with the input and feeds that back to the input to cancel the tendency for the circuit to oscillate. Now, are you ready to talk about your Liberia story, Gary?
Sure.
Okay.
Well, it was in Liberia at the VOA transmitting station. That was my first overseas assignment. And we had General Electric 250,000 watt shortwave transmitters, and we had one transmitter that, okay, intermittently it would like to blow up large vacuum capacitors in the output stage. And with those big transmitters, you knew when something went because it went with a bang. Okay, we had a problem. We'll replace the capacitor, look things over, don't see anything, operate the transmitter again. It's fine for a while, and then bang, and another of these vacuum capacitors go. These capacitors, back in the day even, they were $2,000 each. Oh, something's a problem here. And so none of the indications, all of the instrumentation looked fine. Scoping the output even didn't really give us anything. Come to find out, after we'd gone through about 6 of these capacitors and our stock was being depleted almost down to nothing, we pulled the tube and put in a new tube because we realized that tube was oscillating at VHF. And we couldn't see it on any of our indications because our instrumentation was for HF. But it was oscillating at VHF and blowing these capacitors all to heck. Replacing the tube, and we were good to go. So parasitic oscillations are no good.
Absolutely. So if you have a tube-type amplifier, there will normally be instructions in the manual that tell you how to neutralize that amplifier if you change the tube. I've got a picture here. I think this is the transmitter, isn't it?
That's the transmitter.
That's the transmitter. And I would think that I don't know if you have plans to put one of these in your garage, Gary, but this would be a
No.
great way to break pileups in a contest if you could get one of those. But that's a humongous piece of hardware.
That's at the Greenville transmitting station, but we had the exact same transmitters in Liberia.
Wow. So those are some bad stories about oscillators that, are oscillations that you don't want to have. Now we're going to go into the good ones. There's 3 flavors that are talked about in our chapter: Colpitts, Hartley, and Pierce. These were developed or invented, you could say, between about 1915 and 1923 by 3 different individuals who just happened to be named Colpitts, Hartley, and Pierce. So with Colpitts, here's a circuit, and we get positive feedback via a capacitance divider. You can kind of see that here in the circuit. So how are you going to remember that it's a capacitive divider that causes a Colpitts to work? Well, C for capacitance and C for Colpitts. So that's the way you can do it. Now Hartley, different configuration. Here we're getting feedback through an inductive divider, through a tapped coil, and H for Henry and Hartley. There isn't a pool question that asks you about the feedback mechanism for this one. In Pierce, this is a quartz crystal. We'll be talking a lot more about crystals in a bit. And here we've got a quartz crystal as the feedback mechanism in the oscillator.
P for piezo or piezo, P for Pierce.
Yep, exactly. It's the most stable of the 3. In fact, it's really stable. Back in the good old days when novices were first licensed, they were only allowed to use a transmitter with a crystal oscillator because that would keep the inexperienced novice licensees from transmitting out of band. So Pierce. All right. Let's put another idea in your mind. Pierce, if something pierces your skin, you might bleed, okay? And just hold that thought for a minute. And at this point, let me go to the calculator cam. And I brought some bits and pieces with me tonight. A lot of you may have at least seen pictures. If you're not ancient, like some of us are, you've probably seen this type of crystal. I've taken one apart here, and we've got 2 metal plates, and these press against a piece of quartz, and I couldn't find the quartz, but believe me, there's a piece of quartz that goes between these. It all gets sandwiched in and then screwed together. And in those good old days, hams would actually take one of these apart to expose the quartz crystal, and they could use a lead pencil to slightly lower the frequency of the crystal. Or they could
Toothpaste
to
abrade it to take it higher.
Yep. So hams actually were adjusting the frequencies of their crystals that way. So that's something that none of you will need to worry about. Got a couple of other ones here. This is just another package, a tiny package, another one. And this is actually a color burst crystal out of a TV. And then the one I want to zero in on, other way, is this one here. Now this is a quartz crystal. Let's see if I can get this to focus. There we go. And might be a little hard to see, but here you can see the quartz wafer, and it's broken. You can kind of see it moving around there. So when I said that something sharp could pierce your finger, well, you can associate this with a Pierce type oscillator, crystal oscillator. And this one has got the case unsoldered, which is exposed the innards. Now, I probably broke it taking it apart, but I thought it was a nice demonstration of how they are constructed. So I thought you may enjoy that. Now, there's an effect called microphonics. Now, it's a change in oscillator frequency caused by mechanical vibration. And just like if you were to tap on a microphone, like if I tap on mine, you probably hear that in your audio. You'd hear a tapping sound if you have an oscillator circuit that's microphonic. That's why it's called that. So you normally will never see this in a commercial radio because the manufacturers they've taken everything into account to make it stable. And the solution is to mechanically isolate the oscillator circuit from its enclosure. In older radios, sometimes you'd see oscillator circuits that were mounted on rubber shock mounts inside the radio, and thick metal housings around the oscillator, all to make the oscillator circuit mechanically rigid. So this is something to be aware of. Here's some more pictures. Somebody else took one of these apart. This is what they look like. So a novice might have, back in the day when that was required, might have several crystals that they could use. I had 2 or 3 that my Elmer loaned me, all on 40 meters. Crystal has a very high Q, typically way over 100. They're very stable and precise, which is why they were required for beginning operators. And there's an interesting effect here called piezoelectricity. And I've got a hammer wrapping on some material here. Kind of a joke, I guess, but if you flex the piezoelectric material, it will generate a voltage. So that characteristic is what makes a quartz crystal work, the piezoelectric effect. It's a characteristic of materials that generates a voltage when stressed and that flex when voltage is applied, so it works both ways. Also, it's a mechanical deformation of the material due to the application of a voltage. The pool asks it 2 different ways. Well, you might be wondering, is there any practical application for this other than the quartz crystals that are used for frequency references in radios? Well, phono pickups, you remember record players? Some of them used a piezoelectric needle, not a needle, but the needle would vibrate against a piezoelectric cartridge. Thank you, Gary. There were crystal microphones. You'd pick up a microphone to talk, and the element would be some piezoelectric material. And there were even crystal speakers. So mostly in the older days, these had a lot of applications. But today, you see crystals in virtually any piece of electronics that has a microprocessor in it. And there's an article here if you care to know more. Now, thermal drift is a problem because as temperatures increase and decrease, and you could see this really being a problem in a vehicle installation, so the frequency may drift with equipment temperature. So if you use parts with a low temperature coefficient, and that's spoken to here, in negative, positive, 0 capacitors, that means as the temperature increases, the capacitance doesn't increase or decrease, depending on if the temperature goes up or down. So NPO capacitors can be used. And then in a lot of early 2-way radios, we used crystal ovens. Here's a picture of one. And the way these work, when you first power up your radio, there's a heater element inside the can, and that'll raise the internal temperature of the can up to a certain temperature and then click off, and it'll cycle on and off to keep the temperature within bounds. So typically those would be a temperature higher than you would normally see in operating in the vehicle. So when these came up to temperature, which might only be 5-10 minutes, your transmitter would stay pretty much on frequency. Crystal oven. A little bit of a story. I was at a ham fest and they were giving these away, and I wanted to find one and take it apart so I could show you all what was inside. Well, I must have spent half an hour today looking for these things that I got for free, and I never found them. So maybe a future class will get the benefit of that. But just so you're aware, you pull it apart. There's some. It almost looked like the fabric type material wrapped around the inside, and the heating element, and of course the crystal was in the middle. All right, moving on, a little bit more about quartz crystals. They changed this pool question in a very positive way. The way it used to read was terrible. So the equivalent circuit of a crystal, it's a series RLC in parallel with a shunt capacitor representing electrode and stray capacitance. So when a crystal is actually operating in a circuit, this is how it's acting. This is the circuit symbol for a crystal. One more pool question. To ensure crystal oscillator operates on the frequency specified by the manufacturer, they will tell you a certain value of capacitance that needs to be installed in parallel with the crystal. That's an external part. This is an internal, basically parasitic capacitance inside the crystal case. It's a result of how it's made. This is actually an external part that has to be used in order for it to meet the spec that the manufacturer provided. So equivalent circuit, the parallel capacitor. VFOs, remember I said back in the early novice days you could only use crystals? Well, it was just fabulous when you could use a VFO, variable frequency oscillator. You could do that when you graduated to a general class license. Here's an early night kit VFO. So it uses, you can tune a range of frequencies. Remember our friends Colpitts and Hartley? Well, there'd be one of those kind of circuits in here. And I don't remember if these plugged into the crystal socket on a transmitter, but they would provide an output that you could vary the frequency over the entire ham band. So either capacitance or reductance had to be variable. Capacitance is most common, and certainly not as stable as a crystal oscillator. They drift with temperature, and it was hard to have this accurately calibrated. But that was a wonderful thing when you could change your frequency. Here's kind of an oddball question. For microwave oscillators, even a crystal can wander around enough to make the frequency undependable. So microwave oscillators will use one of these devices to control the frequency. GPS signal reference, also called a GPS disciplined oscillator, rubidium standard or stabilized and temperature controlled high Q dielectric. So there's all of these questions, all of these answer coming up in a question for microwave oscillators. Speaking of which, questions. What can be done to prevent unwanted oscillations in an RF power amplifier? Anybody can unmute and answer.
Charlie?
C.
It is Charlie. Parasitic suppressors and neutralize. We only talked about neutralizing, but the idea of a parasitic suppressor, some amplifiers tend to oscillate at specific frequencies, and you can put LC components in there to trap those. 3 types of common oscillator circuits.
Delta.
Colpitts, Hartley, and Pierce. How is positive feedback supplied in a Colpitts operator? Oscillator. Charlie, through a capacitive divider, Colpitts. How is positive feedback supplied in a Pierce oscillator?
Delta.
Through a quartz
Delta.
crystal, right? A broken piece of quartz can cut you. Which of the following is a technique for providing highly accurate, stable oscillations needed for microwave?
Bravo.
Bravo.
Well, Bravo is correct, but is anything else correct?
Alpha.
Alpha is
Delta.
correct. Okay, it does turn out to be Delta. Yeah, all of these. So we had lots of right answers there, but the one that you'll need for your exam is this one. All of these. What is piezoelectricity? It's a new word that you can use in your next family gathering, and nobody will have a clue what you're talking about.
C.
C, characteristic of materials. It generates a voltage when stressed and flex when a voltage is applied, which crystals use that effect. What is the equivalent circuit of a quartz crystal? May have to read for a minute to figure this one out.
Alpha.
It is alpha, right? RLC in parallel with shunt C, and that shunt C is the electrode and stray capacitance of the crystal, not the external one that we were talking about. Which of the following is an aspect of the piezoelectric effect?
A.
A.
Alpha, correct. Very good. Which of the following ensures that a crystal oscillator operates on the frequency specified by the crystal manufacturer?
B.
Provide that, yes, B, Bravo, provide the crystal with a specified parallel capacitance. What is a microphonic? I love A, but that's not the right answer.
C.
C, changes in oscillator frequency caused by mechanical vibration. Correct. How can an oscillator's microphonic responses be reduced?
Alpha.
B.
It is delta, okay. Now microphonics, we need, those are due to mechanical vibrations. Using NPO capacitors, negative, positive, zero, that stops thermal drift, but they're asking about microphonics here. Speaking of which of the following components can be used to reduce the thermal drift in crystal oscillators?
A.
Now it's A, alpha, yeah, NPO, negative, positive, zero capacitors. Good, we're moving on to the next area now, frequency synthesis. Now there were two flavors over history that were popular. One was phase lock loops and the other was direct digital synthesis. So there's just a couple of pool questions, so this will go fairly quick, this section will. So for a phase lock loop, what is it? Well, it's an electronic servo loop. Servo loop consisting of a phase detector, low-pass filter, voltage-controlled oscillator, and a stable reference oscillator. And I bolded here, voltage-controlled oscillator. So here we've got an oscillator that will tend to be drifting all over the place unless we discipline it somehow. And the way we do that, we have a crystal, which is a reference oscillator, and a divide by N counter. So we're going to be dividing this crystal frequency down and then using a phase comparator to see if the voltage-controlled oscillator is above or below the frequency that we've set by our divider here. So the output of a phase lock loop is a sine wave. It's nothing jagged, it's nice and clean. The only difficulty with phase lock loops is they're always hunting. They're always going slightly above or below the frequency that you've set for them. So this constant hunting effect causes an effect known as phase noise. So with that, let's see what we got here. Allow our radio's VFO to have the stability of a crystal oscillator, a very good thing. And the capture range is the frequency range over which the circuit can lock. So this isn't an infinite, it's a very specific range of frequencies that you'll get the phase lock loop to lock. So the key here, if you can remember voltage-controlled oscillator, because the pool will ask you to differentiate between DDS and a phase lock loop. The phase lock loop is going to have the voltage-controlled oscillator. So as I mentioned, any short-term variations in the frequency will cause phase noise, because it's always kind of drifting around and being pulled back again. And that changing frequency generates what's called phase noise. And phase noise is the major spectral impurity of a phase lock loop synthesizer. There's other functions in addition to just generating a frequency, because think of the case of frequency modulation where the frequency is going above and below a carrier. Well, if you compare that to what's happening here, you'll be able to see that the variation in frequency in the signal will represent the audio that might be impressed on the VHF on that signal. So can do, you can do frequency synthesis, of course we talked about, and FM demodulation. Now right on to DDS, direct digital synthesizer. Now notice the output here, very different. Instead of the nice sine wave that we had out of the phase lock loop, we've got this funny staircase thing that has to be filtered. So in order to create this staircase, we have to have a lookup table within the electronics that will actually put together this shape of a sine wave. And then we have to filter it, and we get our frequency. So what does it use? It uses a phase accumulator in the lookup table. Now the purpose of the lookup table, well, we'll see it down below, a digital to analog converter and a low-pass anti-alias filter. For our purpose, just think of it as a filter. We'll talk about anti-aliasing filters extensively next week. It uses the lookup table containing the amplitude values that represent the desired waveform. So it's putting out pulses, and then it goes to a lookup table and makes something that looks like a sine wave. The spectral impurities are spurious signals at discrete frequencies. Sometimes you might, even on a modern radio, have the antenna disconnected or shorted out and tune up and down the band, and you might hear a signal. It sounds like a CW signal that's just there all the time. That could be a spectral impurity from a DDS, also called birdies, because it sounds like a birdie. So these are like 3 pool questions related to DDS, identifying DDS versus phase lock loop. I tried to give you some things to look for. Right into the questions. What type of frequency synthesizer uses a phase accumulator, lookup table, digital to analog converter, and a low-pass anti-alias filter? Remember the key words I shared. And those key words.
A,
Alpha.
Yep, and direct digital synthesizer. That's the lookup table and the anti-aliasing, the low-pass filter on the output. Correct. What information is contained in the lookup table of a direct digital synthesizer? So the lookup table is used to do what?
Bravo.
It is Bravo. Amplitude values that represent the desired waveform. Now, and how fast we're creating that will cause it to be on one frequency versus another. What are the major spectral impurity components of a direct digital synthesizer?
Charlie.
That's Charlie, spurious signals at discrete frequencies. What is a phase lock loop? What were the key words that we were looking for here? So
A,
did I hear you say C? Well,
It's a servo loop.
yeah, so there's 2 things that say servo loop, but the one that I told you to focus in on was the voltage controlled oscillator, because you've got a nice sine wave oscillator running in a phase lock loop versus the jagged thing that's coming out of DDS. And DDS is the more modern circuit, and pretty much all the radios made today are using the DDS technology versus the phase lock loop. Which of these functions can which of these functions can be performed by a phase lock loop?
Bravo.
Bravo, frequency synthesis and FM demodulation. All right, moving on, mixers and modulators. So here we've got a picture of a mixer. And the electronics, actually, there's some parallels here. We've got eggs here and maybe some butter. We've got different ingredients that we're putting in the bowl, and we're mixing it up, and we're getting something different as a result of the mixing process. So that's actually an analogy that fits to some extent. So mixers are used to change the frequency of a signal in a receiver. Mixers are used to convert to the intermediate frequency. Can also be used to change frequencies in a transmitter. We'll definitely be seeing this next week. And spurious mixer products are generated when input signal levels are too high. Now, I know Gary was teaching us about mixer math in another, I think, the general class. So the mixer output going to be the two input frequencies and the sum and different frequencies. So those are the ones that we're interested in. So diagrammatically, here we've got an RF signal coming into our receiver. We've got a local oscillator. And in the output of the mixer, we're going to have some amount of the receiver energy, the signal being received. We're going to have some element of the local oscillator going to sneak through the output. But the thing that we're really interested in is the sum and difference frequencies between the local oscillator and the received signal. And then what we will do is use a filter to select the proper output frequency. So the RF might be 146 megahertz, then the mixer output will be something a lot easier to amplify, maybe 10.7 megahertz, for example. So it's very difficult to amplify the 146 megahertz signal to the level that you need to have good sensitivity. So let's look at the blue text. Too much in will cause all kinds of junk to come out. And the sum and difference frequencies are key. Modulation. Okay, now if you could imagine, let's look first of all at the modulating sine wave. This would be speech. A sine wave is shown here. But if you want to talk to somebody that's in your next door neighbor, you can shout loud enough to be heard, okay? But if you want to talk to somebody in another state, you can't shout loud enough to be heard in another state. So to make that happen, you have to send a radio wave which will travel and make it to the other side of the state. Well, that's nice, but in order for that person on the other end to have any intelligent content, somehow we have to superimpose this speech onto the carrier wave in order for it to travel to the place we want it to go. So modulation is the process of adding information to an RF carrier. Why is it a carrier? Well, it's carrying that signal to where we want it to go. So that there's a term that can be very confusing. That this is in the context of the pool. Baseband is the frequency range occupied by the message signal prior to modulation. So that would be this waveform here. So you can think of this in a single sideband case as being voice that you'd be transmitting. That's the baseband. Now baseband is much broader than that. It can be digital tones. In terms of microwave, it can be multiplexed audio signals. Anything that you're going to superimpose on the carrier to send it far, far away is the baseband. Now amplitude modulation contains a carrier and two sidebands. We've seen that before. And the amplitude of the signal depends on the amplitude of the audio signal. They've only given us baseband to remember here. And here's a picture. So here with AM, we've got a carrier signal, and we have an upper sideband and a lower sideband. And single sideband is a form of AM signal. And there's two ways to create it. We've got the filter method and the phasing method. The filter uses a circuit called the balanced mixer. Balanced modulator. Thank you, Mr. Gary. What does a balanced modulator do? Well, it suppresses the carrier. So the carrier goes away and you're left with the upper and lower sideband, which is also called double sideband suppressed carrier, if anybody cares. Balanced modulator removes the carrier. A bandpass filter removes one of the sidebands. That's the filter method of generating single sideband. And again, as I said, it's a form of AM, and they've just taken out some other stuff. Then there's called the filter, or the phasing method, or the quadrature method. We're going to be looking at this a little bit more next week. The phasing method, the math behind how that works is extremely complicated. If there's anybody that wants to know, I gave you an article you can read. I recommend that most of you don't. It'll make your head hurt. So the quadrature method uses 90 degrees, 92 signals, 90 degrees shifted in phase, and they use magic math inside the digital signal processing circuitry to actually create the sideband signal. It's very hard to do with an analog circuit. It has been done, but it's very difficult. Very easy to do with digital signal processing. There's a mathematical function called a Hilbert transform that actually achieves that. And the quadrature method is usually employed in radios using digital signal processing, which we'll talk a lot more about next week. So the filter method and the phasing method. That was quick. What are the principal frequencies that appear at the output of a mixer?
Charlie.
It is Charlie. The two input frequencies, which is in a receiver, it would be the RF signal you're wanting to listen to, the local oscillator, and then out of the mixer are the sum and difference frequencies. And you'll pick one of those and amplify it. What occurs when the input signal levels to a mixer are too high?
Alpha.
Alpha. Spurious mixer products are generated. So you not only get the sum and difference frequencies in the two inputs, but you get all kinds of intermodulation frequencies as well. What is meant by the term baseband in radio communications?
Bravo.
It is Bravo, the frequency range occupied by a message signal prior to modulation. The easiest way to think of that is single sideband. It'd be the 300 to 3,000 hertz range that gets passed in sideband. What is one way to produce a single sideband phone signal?
Alpha. Alpha.
Correct. You use a balanced modulator followed by a filter. The balanced modulator gets rid of the carrier. The filter gets rid of the unwanted carrier. Sideband. Yes, I need somebody to keep me honest. All right, frequency and phase modulation. Some real interesting concepts here. So here we've got an FM signal. Here's the carrier. Here's the speech. And notice that these the carrier's getting all bunched up here and spread apart here. So what's happening is the frequency is changing in accordance with the applied input signal. So I've got about 3 little facts here, but they'll all join together when we get to the end of this. So a reactance modulator, and the way that they've done the pool this time, they tried to use a generic question that would apply to both phase modulation and frequency modulation. That's why it's worded this way. So a reactance modulator produces FM, frequency modulation, or PM, phase modulation signals by varying a capacitance. Remember last week Gary introduced us to the varactor diode. That's the case that we'll use here. Here's some circuit symbols. The one in our book is this one. Gary showed us this one last week. Remember how that works? If you reverse bias a PN junction, this depletion region will get bigger depending upon the voltage that you apply to it. Well, that's separating the plates. If you consider the P and the N material as plates of a capacitor, they're getting further apart or closer together. So typically a varactor diode is the device that's used in a reactance modulator to make this true. So we've got 2 flavors of FM. We've got direct FM and indirect FM. FM phone signals can be generated via reactance modulation of a local oscillator, usually with a varactor diode. So we're actually changing the frequency of the oscillator itself. Indirect FM, which is also called phase modulation, uses a reactance modulation to vary reactance in a tuned RF amplifier. So how does that work? So it's going to shift the phase of the signal And shifting the phase of the signal is actually the same as varying the frequency. That's why phase modulation and FM kind of all fit into the same bucket. Now get ready and buckle your seatbelt. FM and PM sound the same on the receiving side, and then I added these words, sort of. And what I'm going to tell you is phase modulators actually distort the audio in a very specific way. So a little bit more, Kessler's diagram here. Direct FM is going to modulate the oscillator directly, change the frequency. So here we've got the audio in, and we're actually applying that audio through our reactance modulator directly to the oscillator, shifting its frequency up and down. Then we've got phase modulation, also called indirect FM. Indirect because we're not directly changing the oscillator. We're going to modulate a stage after the oscillator, some kind of a tuned RF stage. So here we've got, in this case, we're introducing a variable frequency delay with a reactance modulator, which is kind of the same as shifting the frequency. That's why they're both, you can consider them both FM, direct, changing the oscillator directly, or indirect if you're changing the phase relationships in a tuned circuit beyond the oscillator. And as I said, phase modulation distorts the modulated audio in a very specific way. With phase modulation, as the audio frequency goes up, the amount of modulation increases. So that would be kind of a problem on the receiver side, because if the high frequencies are much louder than the low frequencies, it's going to sound terrible. Okay, we don't have that with direct frequency modulation, but there's fixes for that. We'll talk about those next. That concept is pre-emphasis and de-emphasis. So phase modulation or indirect FM boosts the higher audio frequencies. It's just a part of the physics of the way a phase modulator works. With direct FM, we're going to do something to the signal to make it look like phase modulation. So where with phase modulation, we were getting the effect for free of increasing the higher frequencies compared to the lower ones. With direct FM, we're going to put a circuit, an LC circuit or an RC circuit in there to boost those high frequencies. Okay, now what we have is on the receive side, they both sound the same, but they're still all out of whack, right? Because the high frequencies are much more emphasized than the low frequencies, and we don't want that. We've just, by doing this magic, caused it to leave each transmitter looking the same. So here's a pre-emphasis curve. Of course, with radio, we only have 300 to 3,000. This is more of a broadcast picture, but pre-emphasis, we're emphasizing the high frequencies. And then what we're going to do on the other side is we're going to have a de-emphasis filter that's going to reverse this effect. So here's another diagram. It's a different kind of pre-emphasis and de-emphasis. Here's the pre-emphasis. And then on the receiver side, we have a de-emphasis circuit. And what do we wind up with? Flat audio. So de-emphasis is commonly used on FM receivers for compatibility with transmitters using phase modulation. And without all of this explanation, that's a little hard to understand, because you get the boosted high frequencies for free with a phase modulator. You have to do it on purpose for direct FM, and when that is done, you've got the same thing arriving at the receive side, and it'll flatten it out. De-emphasis also reduces high frequency noise. When FM broadcast first got started, it was known to be a very quiet medium. Classical music was a really big deal back at that time, And to be able to hear classical music without noise in the background was a major selling feature for FM. So it's also used in broadcast audio. But because the indirect or phase modulation is so much easier to do, we typically always have, that's usually the mechanism that's used in our FM transmitters, think 2 meters primarily. So with that, let's move on to detectors and demodulators. Okay. So here we've got a metal detector, all right? So how does this relate to what we're talking about? Well, the thing of value is hidden under the ground. You can't see it. We somehow need to find it and extract it in order to have something valuable. So a demodulator is used to recover information from a modulated signal. You can't hear the RF. It's way too high a frequency. But if we can extract that information that was impressed on the carrier, we'll be happy campers. So we've got a diode envelope detector. That's the first one for detecting AM. And I'll show you a demo here in a second. So it works by rectifying and filtering the RF signal. That's for AM. So here's an AM signal. If we can rectify it, notice the positives and negatives are going to kind of cancel out. If we rectify it with a diode, we're going to wind up with this. And then if we filter it, we'll just have the audio left over. So I tried this earlier and it didn't work, but because we don't have any strong AM stations near Gary. This worked fabulously when I was home. So this is more Hamfest material. So what we have here is a coil and a capacitor. We have a diode here. And the capacitor will help tune the circuit. And normally they use high impedance headphones here. I've got a resistor in place of that, and a little Radio Shack amplifier. I'll turn that up. And if there were an AM signal, we could tune here and actually be able to hear an AM signal. I'll try a different combination of inductance. Well, no joy right now. It didn't work before class either, but at home I do have a strong AM station, and I was able to hear it. And the way this works is the diode, which is the detector, rectifies the incoming AM signal, and you can actually hear it. So when I found this at a Hamfest, I had some friends at the Hamfest, and I told them that I don't need my fancy transceiver anymore because I've got this wonderful new crystal receiver, but nobody believed me, which is a good thing. So the next couple slides are going to be bits and pieces about FM and single sideband, which we're going to go through because it has the exact information from the pool contained therein. And then I've got a couple of summary slides because they've picked bits and pieces. It's really hard to associate them into the right answers for the pool. So I'm hoping that this will help with that. So first of all, a product detector, that's what's used for demodulating single sideband signals and things that are related. And it uses a locally generated carrier. Remember, with single sideband, we suppress the carrier, we don't transmit it. But that has to be added back in again in order to detect the audio. So that's done with what's called a beat frequency oscillator in the receiver. So a product detector is used for demodulating single sideband. For FM, we're going to have what's called a frequency discriminator to detect FM. And the electronics behind some of this is in our license manual. For now, the pool committee is just wanting you to be able to associate the detector type with the kind of modulation that you're going to be decoding. And next week we're going to be looking at SDRs, software-defined radios, where an RF signal is mixed down to baseband. for analog to digital conversion, and then information can be demodulated using software, magic in software. So these are the keys for now. Now, modulation of single sideband. Remember we talked about the filter method, balanced modulator, the phasing method we've talked about. And as said previously, the demodulation for single sideband, we use a product detector. Now the FM case, here's our FM diagram. We're going to change the capacitance with a reactance modulator, varactor diode of an oscillator. This is a review. As was this, we're repeating some things that we saw before, but now we're going to be relating them side by side, which I think will be a big help in answering the pool questions. So FM, we're changing the capacitance with a reactance modulator with both the direct FM and the indirect or phase modulation. So we have the two ways of creating FM, direct and indirect. Doing it with a reactance modulator in both cases, just at a different point in the circuit. And for demodulation, we're using a frequency discriminator. So I'm hoping that these summary slides for single sideband and FM will help you with the next series of questions. Which of the following can be used to generate FM phone signals? We saw there were two ways. They're going to give us one in the answers. Generating FM. Well, if you don't know, guess.
B, Bravo.
It is Bravo. Reactance modulation of a local oscillator. Correct. Okay, what is the function of a reactance modulator? And here they're giving us the generic case.
Delta.
It is delta, produce FM or PM by varying a capacitance. Normally that's done with a varactor diode also. What is added to an FM speech channel to boost the higher audio frequencies?
Delta.
Delta, we're pre-emphasizing the higher frequencies, and that would only be in the case of the direct FM case, because we get it for free, so to speak, with a phase modulator. Why is de-emphasis used in FM communications receivers?
Alpha.
I think I heard alpha for compatibility with transmitters using phase modulation. The reality is it's also for compatibility with direct FM that has been pre-emphasized. So it's really both cases, but this is a true statement, and it's the only one that is true of the ones that are given here. What is a frequency discriminator?
Delta.
It is delta. You have frequency modulated signals, frequency discriminator, they kind of go together. That's correct. Or Gary used to say that FM listeners are very discriminating. That's back when it was classical music, I guess, or primarily. How does a diode envelope detector function? That's my magic crystal receiver I tried to demonstrate that didn't work because we don't have any AM stations close to the house.
Alpha.
It is alpha, right? That would be for detecting an AM signal. What type of detector is used for demodulating single sideband?
Charlie.
It is Charlie. It's the product detector. That's why I did the summary slides to kind of reinforce that. Okay, well that finishes up Chapter 6, Part 1. So for next week, we want to finish the chapter. That's sections 6.3, 4, and 5. I'll be sending an email on that. And I think Gary has a very special announcement, if you have time to do that.
Yes. So a little bit of background, though. First, I'm a transmitter guy. Okay, I used to work for Voice of America for 20 years, and we used statistics to measure our performance at the transmitting stations. We measured our irregularities. If a transmitter tripped off and then came back on again, that was considered an irregularity. Or, God forbid, if we were not able to bring the transmitter up on frequency at the right time with the right programming, that was an outage. And of course, with Hurricane Helene that came through here, we had an outage of a couple of weeks here, at least of 3 weeks actually, for the extra class. So my exciting news as a transmitter guy is that, and remember the outage was caused by the fact that we didn't have internet uplinking or uploading capability from Charter Spectrum. So follow me over if you would, Bruce here. We now have something added to our mix. We now have Charter Spectrum. They're still our main internet service provider, but we now have Starlink as well, which is up and running. Both are connected to my prosumer router, a TP-Link Omega, and it will actually automatically switch over from Charter to Starlink. It takes about 40 seconds, so there still would be an outage in there, but so we won't miss any more future programs. So I think that's exciting. So we're going to bring you the class on time, no matter what. And even if we have a power outage, we have the solar system with the batteries, we're still going to be here. So that's my news.
All right, very good. So you can super source us for a second there, Bruce. And
As I sit down.
as you sit down, get back in frame, and if there's
Any comments or questions from
Exactly.
anyone before we go? Let me just unspotlight us here. I think you wore them out, and we have competition tonight.
We do, yes. There's something,
Something
going on in the world that's distracting people. I
Right.
can't imagine what that might be.
All right. Well, next week,
Yep,
the last half of Chapter 6.
yep,
Until then, Dave, I think.
yep, absolutely. Thanks,
73,
everyone.
y'all.
Thanks, everyone.
See you next week.
Thank you. I'll be back. 73, thanks.
All righty.